Today we're going to be presenting this paper uh, uh, towards deep learning models resistant to adversarial attacks, uh, presented by me, Thomas Cummings, and my group member, Lindsay Erickson. So in this presentation, we're going to talk about security against attacks, the saddle point problem, local solutions to the saddle point problem, network capacity and robustness, the experiments and results, conclusion, and finally points for and against the paper. So the first part is security against attacks. So the authors in this paper, they make a distinction about model robustness. The first way to look at it is robustness against a specific attack, such as fast gradient sign method or projected gradient descent. However, the authors suggest that we look at model robustness against a specific class of attacks. So this is slightly different than current work, which focuses on a specific attack algorithm or a specific defense algorithm. So when it comes to security, we'd like some guarantee that our model will be robust against not just one specific attack, but against a class of attacks. And so in this paper, we're looking specifically at the class of attacks known as first-order adversaries. So a first-order adversary is an adversary that has white box access to the model. So they have access to the network parameters, which allows them to use gradient ascent on a loss function to find adversarial examples with high loss. So this class of attacks encompasses several of the attacks that we've seen in this class. All right. So they formulate security as a min-max function. So this is the min-max function. So we'll see here on the right, there's a loss function that you should be familiar with. It's taking in a training sample X and a perturbation delta and comes up with the loss. And this part here, it maximizes the loss by finding the delta within a threshold S. So this term here, this is the adversarial loss, and it describes how strong the attack is on the training sample X. An attacker tries to maximize the adversarial loss for each image by picking the best delta to perturb the original image. The higher the loss, the more likely the adversarial image will fool the network. Next, we're going to look at rho theta. This function describes the average expected loss over the entire data set. By looking at the average loss, we can expect for each image, we get an idea about the strength of the adversary. So you can think of this as the amount of damage that the adversary can do. So robust networks, they want to minimize rho theta. So this right here is what the robust networks want to do, and they want to minimize rho theta, and then adversaries, they want to maximize rho theta. So this creates a min-max problem, which can be it can be modeled as a saddle point. So why does the saddle point matter? So what do we get when we solve the saddle point problem? So it gives us some idea on the strengths of adversaries and on the limits of robustness of models. So we're trying to answer some questions. Can we create attacks that always find adversarial examples? Just how powerful can future attacks be? Can we create robust networks that make adversarial examples hard to find? And is it possible to make a network with no adversarial examples? So this is a cute picture of what the saddle problem looks like. So it shows how the saddle looks like someone riding a horse. And this point right here is the optimization of the minimum and the maximum right here. And this is where the rider would ride. All right, so to understand the saddle point problem, it's helpful to break the min-max problem into two components. The first is the inner maximization problem. where the adversary seeks to a point at the top of the model. The adversary seeks a point at the top of the model. So here we're looking at a graph of loss, and the adversary wants this point here of maximum loss. And then the second part of the model is the outer minimization problem. So this is where the robust model is trying to minimize the loss. So it's trying to get a point here at the bottom with the minimum loss. And so we end up with something like this, where we've got the outer minimization problem. So the robust network is trying to minimize the loss here. And then we've got the inner maximization problem, where the adversary is trying to maximize the loss. And you find the solution to this is somewhere here in the saddle point. However, the actual saddle point is not nearly that simple to solve. So the saddle point problem, it has the inner maximization problem for the adversary. It maximizes adversarial loss, and it's difficult to solve because it's non-concave. So there's local maximums, and they make it difficult to solve. So similar to the outer minimization problem, the model is trying to minimize the adversarial loss. However, the problem is non-convex because there are many local minimums. This makes solving the saddle point outright very difficult. However, if we were able to solve the saddle point problem, and if we solved it and found that the adversarial loss is close to zero, then we can conclude that the model is robust and attackers pose little or no threat to the model. This would be a definitive way of demonstrating that the model is robust to first-order attackers. Again, first-order attackers, they have access to the network models, and they can use gradient ascent to find adversarial examples with high loss. So yeah, and our goal then is to optimize this so that we can find robust parameters where the model is robust. And yes. All right, so exploring the saddle point problem. So the authors go and they examine the saddle point problem to look at the local maximums. And they start by exploring what the loss looks like around a training sample. So they did this by running PGD 10,000 times with starting spots uniformly placed around the training sample. So they picked 10,000 places close to it and within the L infinity ball. And they did this at all these starting locations to find adversarial examples. So what we see here is a graph of 20 runs of PGD. So here along the bottom, we see the iterations of PGD, and here we see the loss value. And so we can see that as the PGD iterations increase, the loss value increases for all of these. One thing to note is that if you look at the final loss values, see it goes up and it starts and then it plateaus. So all the final loss values end up in this group here. And the same is true for CFAR 10. So we see as the iterations increase, the loss goes up, and all of the adversarial examples end up within a small range of loss. So then the authors, they look at what happens when you train the network with adversarial images. So this is a similar graph, and we see something similar where at the beginning we've got low loss, and as the iterations increase, the loss goes up. And all of the loss values end up in about the same range. And the same is true for CFAR 10. The values are even more tightly coupled for CFAR 10. And what they find is that the loss values here are much lower than the training with the training data. So the local maximums all have about the same adversarial loss, both for standard training and adversarial training. And adversarial training reduces loss for all local maximums. So let's see, we can look here. So this is another view at this. So here we've got 5 separate training images, 5 for MNIST and 5 for CFAR10, and they run PGD 10,000 times. And this shows here the loss value and how frequently we see that loss. And so the blue is the standard network trained on the original training data. And we can see that the loss values, again, they're all clumped up into this range. So they're clustered together. And we see that for all 5 of the examples, both on MNIST and on CFAR10. And then we look at the adversarially trained network. So once we train the network with the adversarial images, they run PGD, again, 10,000 times within the L infinity ball around the training sample, and they get a new set of losses. And these losses, they're significantly smaller and they're more tightly coupled. And we see that in every single one of these. So what they're showing is that one, all of the loss values, the local maximums in this saddle point problem, they all have about the same value. And so you can expect that they're going to be in the same range, and there aren't any extreme outliers. And then they show that if you train with those adversarial images, so if you adversarially train the network, then the loss value decreases for the entire group. So all of the local maximums end up having a decreased loss. So the saddle point summary. All right, so so here are the takeaways from the saddle point that the authors find. So the saddle point problem, it's difficult to solve because of local minimums and local maximums. However, the authors show that the saddle point is tractable and can be solved locally. So the authors, they conclude that PGD is the most powerful adversary given first order information about the network. Again, so first order adversaries, they have white box access and they're using gradient ascent to find adversarial examples with high loss. So PGD is a solution for the inner maximization problem of the saddle point. So the authors, they empirically find that all adversarial images have about the same adversarial loss.
So Thomas, so
yes.
These 2 points, the authors conclude PGD is the most powerful adversary given, then PGD solution and then maximize it.
Yes.
So those points you haven't talked about yet, is that right? That's next you are going to talk about.
Yeah. So yeah. they don't prove that that PGD is the most powerful attack, but they find evidence that it is. So because they used PGD on so many spots around the training sample, they showed that the adversarial losses, they're all in the same value, and if there are potentially other adversarial examples that are higher value, and they don't prove that there aren't, but they're showing empirically that it's difficult to find adversarial examples with high loss that PGD won't.
Yeah, I understand that. What I'm saying, like especially the third bullet, in your presentation so far, you haven't demonstrated that PGD is the most powerful. It's going to happen, is that you're going to talk about that? Yeah,
we're gonna show later some more evidence about.
Yeah, that's what I was saying. Yeah. Okay. Good. Yeah. Continue, please.
Okay. And so they show that by adversarial training they can solve the outer minimization problem, because by adversarially training they lower the maximums for all of the adversarial examples. And then we'll talk more about network capacity and robustness.
Okay, so now we're going to talk about network capacity and robustness. So to show what is meant by robustness, the authors show here a simple linear boundary that successfully separates 2 classes. However, when adversarial examples are added, and here the squares around the data points are the L infinity balls, and as Tom mentioned earlier, there are many adversarial images inside each of these boxes. Anyway, you can see that this linear boundary is no longer sufficient at correctly classifying these images. You can see that.
Lindsay, can you use a cursor and show what you're talking about?
Sure. Okay. So here are these red stars. You can see that it's starting to go over the boundary, the linear boundary, and misclassifying these examples. So the last figure shows a boundary that is able to classify images correctly, which is this red squiggly line that perfectly goes around these examples. And though this is a very complicated boundary, it's exactly what we want as it's robust to adversarial examples. So in an attempt to show how to create a robust classifier, the authors tested capacity to see if it would achieve robustness. So the authors took a simple CNN using the MNIST dataset and tested the accuracy of different network capacities. And after each run, they doubled the size of the network and retested. So the first figure here shows standard training on natural examples. As expected, there's a low accuracy for classifying FGSM examples and PGD examples, which are the two bottom lines. What's my cursor at? Two bottom lines down here. While there's a high accuracy among the natural examples. However, it should be noted that as the model capacity increases, the accuracy among the adversarial examples also increases right here, but only slightly. So the second image utilizes FGSM training. And as you can see, as network capacity increases, it can successfully classify FGSM examples, which is this red line on the top here. However, it does a terrible job at classifying the PGD examples, which is the brown line on the bottom. The authors mentioned that FGSM training overfits the FGSM examples due to the restrictive nature of the produced examples, hence the high accuracy among here. So the third image utilizes PGD training. And as you can see, as the network capacity increases, accuracy among all training images, FGSM generated images, and PGD generated images all increase to greater than 80%. However, this isn't achieved until we get a sufficiently large network. So you can see the jump between 2 and 4 right here. The last image shows the training loss among the adversarial examples that the networks were trained on. And the decreases in loss as the network capacity increases shows that the value of the saddle point is decreasing, meaning that the model can better fit the adversarial examples. So the authors also tested this capacity on the CFAR10 data using ResNet network. After each run, they increased the width of the network by a factor of 10. And what they found was that increasing capacity had the same characteristics as increasing the capacity on the MNIST data using a simple CNN. So the first figure here shows that for standard training, the wider network had a higher accuracy. And as expected, the network had a high accuracy among natural images and lower accuracy among the FGSM examples and the PGD examples. And then looking at the FGSM training again on this second table, there's a high accuracy among the FGSM examples for the wide network. However, if you look below, the PGD examples only have a 0% accuracy there. So for this third table, the PGD training, again, shows similar results to the wider network was able to produce high accuracy among natural images and a reasonable accuracy among the FGSM examples and the PGD examples. So as you can see here, there's a 56.1% and 45% or 45.8% on those. So the last image, again, shows the training loss, showing that it decreases as the width of the network increases. Oh, sorry about that. So for all instances here, we see that the performance benefited from increasing the width of the network. So from these two examples, the authors observed some interesting characteristics. First, capacity alone helps. We saw this by observing the accuracy as the network capacity increased in the last two slides. Second, FGSM adversaries don't increase robustness, and we saw this by noticing the poor robustness in FGSM training among the PGD examples in the last two slides. and also saw that the natural images had lower performance than FGSM examples with FGSM training on the MNIST data. Next, weak models may fail to learn non-trivial classifiers. And we saw this in the PGD training example, where there was a big increase in accuracy for natural images, FGSM examples, and PGD examples after increasing the network to a larger size. The value of the saddle point problem decreases as we increase the capacity, and we saw this by noticing the decrease in loss as the networks grew. And lastly, more capacity and stronger adversaries decrease transferability. The authors found that this reduces the effectiveness of transferred adversarial inputs. So now moving on to experiments and results. So from their current observations, the authors focused on two key elements. First was to train a sufficiently high capacity network, and second was to use the strongest possible adversary. So due to the good observations on PGD adversaries that we just saw, the authors chose to use PGD as their adversary for their examples. So to confirm they're solving their saddle point problem, they show that the loss value decreases when training against their adversary. This decrease in loss as iterations increases shows us that the model is minimizing the adversarial loss and solving the outer minimization problem, resulting in a robust model. But interestingly, because Tom showed you this figure earlier, showing that iterations increase as adversarial examples, or increase on adversarial examples, and the loss value increase, meaning that they were accomplishing the inner maximization problem. So this slide shows that they were able to solve the saddle point problem by showing us their results on the inner maximization problem and the outer minimization problem. Now the authors evaluate trained models against a number of different adversaries. So they consider their white box attacks being attacks with PGD, attacks with PGD using Carlini-Wagner loss function, and black box attacks of attacks from independently trained copy of the network, attacks from version of the same network, and attacks from a different convolution architecture. So testing these adversaries on the MNIST data set, we see the following. So in this table, they consider white box attacks with PGD, and we can see the accuracy among all PGDs here had the best performance, while PGD with 100 steps and 20 restarts had the most successful attacks. So the next box, the next table considers black box attacks with independently trained copy of the network. Here we can see again that PGD had the most successful attacks. So there are these two right here, but we see this 100 steps and 20 restarts had the most successful runs, or the most successful accuracy. So the last table considers a black box attacks with different networks, and we see that FGSM had the most successful attack performing, or right here, and it performed better than PGD in this example. So if we now testing the adversaries on the CFAR10 data, we see from the top table, using white box attack with PGD, PGD again had the most successful attacks, just like the MNIST data. And from the second table, using the black box attacks with independently trained copy of the network and black box attacks from a version of the same network trained only on natural examples, we see that again, PGD had the best performance and the most successful attacks. So the authors mentioned that they weren't really happy with these CFAR10 results as they were with the MNIST results, and mentioned that possibly increasing the network size could make the CFAR results better. So next, the authors wanted to test the resistance of L-infinity bound attacks for different values of epsilon and test the resistance of their model to attacks that are bounded by or bounded in L2 norm. So in this first graph right here, looking at the MNIST L-infinity, they show the accuracy of various levels of epsilon on adversarially trained networks against PGD attacks. This vertical red dotted line right here, it indicates the epsilon value that the model was trained on, which is 0.3. And you can see that epsilon values less than 0.3 had pretty good performance. And right now we're looking at this blue line, which is a PGD adversarially trained network. And you can see that once we increase epsilon to be greater than what it was trained on, there's a big decrease in performance. It just drops way down. So the authors mentioned that this drop in performance could be because the learned threshold operators are tuned to the epsilon it was trained on. So the second graph right here shows the L2 bounded attacks on MNIST. And looking at the blue line again, which indicates PGD trained networks, you can see that the accuracy decreases as epsilon increases. And though the authors found that the decrease in accuracy was due to the fact that large values of epsilon produced perturbations that could potentially change the ground truth label. So what they mean by that is when you look at this, these are, right here, this is an illustration of what they mean. These are adversarial examples with L2 norm bounded by an epsilon of 4. So as you can see, the perturbations can easily be misclassified by a human. So this first one here on the left, I mean, a human could potentially misclassify that as a 7, and this one on the right could potentially be misclassified as a 4. So in the second chunk of graphs right here for CFAR 10, they did the same experiment for it, for testing the epsilon on the L infinity norm and testing the L2 norm. And this showed similar results to the MNIST experience, showing that, you know, it decreases, both of these instances decrease as epsilon increases, though it is a lot smoother than the MNIST decreases. So in conclusion, the authors found that optimization problem is tractable. Model capacity has an impact on adversarial robustness, and they can achieve the highest levels of accuracy against the strongest adversaries.
All right, so points for the paper. So the first point is this paper, it looks at the big picture of security and not just at a single attack or a single defense. And the saddle point problem, it's broad enough in scope that it will apply to future attacks of first order adversaries. So as new attacks are discovered, the attack itself can be used to strengthen the model using adversarial training. However, the authors, they advocate that PGD is universal when it comes to first order attacks, which have white box access to the network parameters. So new attacks that use gradient ascent on the network's loss aren't likely to be more powerful than PGD. So the authors, they created 2 challenges on GitHub for MNIST and CFAR 10. They're putting their work on the line by making it into a challenge and encouraging others to defeat their model. So this is it's a great role model for how adversarial papers should be published. And they have kept up with the challenge for the last 3 years, having accepted a new submission as recent as last October. The way the challenge works is that for the first few months, they offered the challenge as a black box attack. So they released the training code for the network, but not the network parameters. And then after a few months, they released the model parameters so that they could attempt white box attacks. So they had a few submission attempts on black box attacks from MNIST, and the best submission was able to reduce the model's accuracy from 96 to 92%, which isn't really very much. So the next point is the model they trained for MNIST, it's strong. So they received 11 submissions in the last 3 years, and their robust model, it's only lost 1.5% accuracy. So going from 89.6% to 88%. So the CFAR 10 challenge, it received 5 submissions. The CFAR 10 model, it started from a less robust standing point as the MNIST model. But again, the authors, they mentioned that there are things they could do to improve that, such as increasing the network capacity. But the CFAR model, it's only lost about 1.3% accuracy in 3 years. And finally, their proposed defense, it's simple. So they solved the inner maximization problem using PGD and solved the outer minimization problem by training against the adversarial examples created by PGD.
So against the paper, the authors focused their work on L infinity bounded attacks. They tested L2 in some cases, but didn't consider other norms. Their results are not as promising for CFAR 10 as they are for MNIST. They mentioned increasing the size for CFAR 10 to see if it performs better, but didn't test this theory. The authors only considered first order adversary attacks, such as PGD. It's unclear whether we can find a good solution to the saddle point in a reasonable amount of time. And lastly, networks must be sufficiently large to be robust against attacks.